this problem. This is in the book. But why do we care about these kinds of things? This is one reason right here, okay? By the way, you'll notice whenever they pour a sidewalk, they always put etchings in it, long lines in it that have a V, and that is because they expect it to expand, and rather than have it crack randomly somewhere on the sidewalk, they're wanting it to crack right along this joint. So that's why they put those V's in there, so that if it does expand and break, it breaks in the V and it still looks nice. Okay. You'll also see sometimes they'll put, oftentimes like cardboard or some kind of expandable or squishable material in between the pour, so that when it stretches or shrinks, it's got something to push against that's flexible and not hard. So you do have to consider all these things when you're pouring concrete or building the Eiffel Tower or any of those sorts of things. It's going to stretch. It's going to contract based on the changes in temperature. So we have to account for that. And that's what this is implying, right? Oops, we didn't leave enough room, right? And my concrete expanded more than the room I have available, so it pops up. You've probably seen that. Maybe. Usually it's tree roots that get underneath it and pop them up, right?
I actually saw the accident on Red.
What would they be? They're probably some kind of steel, right?
Yeah.
Railroad tracks are made of steel typically. Okay, so you have to account for this idea that they stretch. If you don't put expansion joints on there, your rails will buckle and the trains will derail and so on and so forth. Similar idea here, we're not going to do this, but you can imagine if I have concrete supports with a beam, the beam is going to stretch. We need to make sure we left a little bit of room here so that we can account for that. How many people have ever put down sheets of different metals expand at different rates? How many of you have a thermostat at your house? Okay, there are two kinds. There's mercury thermostat. Well, they all work on this bimetal spring idea. But if you're interested, you can carefully take the lid off your thermostat and you can look in it, and typically you'll see this wound bimetal spring, which means bimetal meaning two metals that are fused to each other. And so here's a case where we have brass and steel. Let me back up a second. I think brass is 19, if I remember correctly. Brass is 19 times 10 negative 6, and what was the other one?
Steel.
Steel is 12, right? Yes?
Mm-hmm.
Am I reading that correctly?
Yeah.
I am. So let's go back to our picture of our bimetal spring. So if life is good and temperatures are equilibrated and there's nothing going on, and then all of a sudden we heat it up, realize brass will expand faster than steel, so it pushes it this way because it's expanding faster on the left than it is on the right. And also it will contract faster. It goes both ways. It contracts faster than steel, so the piece of metal will bend in the opposite direction. Those wound up springs are bimetal springs, and when the temperature in your house changes, the needle moves back and forth and it trips your thermostat to turn the heat on or turn it off, or AC if you have it, I guess.
It also happens with toasters. That's how they do the little timer on the knob.
I
I think. I'm pretty sure.
I think that is just a plain old spring. I don't think it's heat related. Yeah, it's just, I don't think it depends on the, yeah, so you have bimetal switches in a variety of things. Anybody have one of these teapots where you press the button and it boils and then it clicks off by itself? That's what's going let's see, let's take a break and we'll come back and talk about this.